and having the chance to show my work or our work on tunnel junctions. So I will start a bit abrupt, so we don't have much time. So come on, should work. So I will start short with the motivation. I will talk about tunnel junctions. So it's something which is starting actually to go away from our community radar. So it's not anymore so popular, and I think it's still a topic we should have a look on it. It's interesting physics. Also device and fundamental physics here. And I'm trying actually just to highlight a couple of things here. So, what are these ferroelectric tunnel junctions? It's very simple. Conceptually it's very simple. If we have two metals on a ferroelectric or an insulator, so if this insulator comes very, very thin, then there is a certain probability that the electrons from one metal will tunnel into the other metal. In other words, there is a let's say tunneling effect which occurs at that very, very low thicknesses. So that's a very important tool actually to test the ferroelectricity for very small or very thin ferroelectric layers. So I don't think there is something else which is so good than this analysis of the tunnel junction when it's about analyzing ferroelectricity at a low dimension. So what's all about is in principle the effect of the polarization on the barrier the metal forms at the interface with the ferroelectric. So ferroelectric, if you take it very general, it's a wide bandgap material. So either wider or not. So it's something which is anyway having at least one EV, common ferroelectrics, and can go up to 5 EV. So there is a barrier which forms automatically between those two metals. So, and if you are having a very, very thin, you are coming down with a thickness, you definitely you are in the full depletion condition. So that means you don't have any thermal activated carriers in. So, and it's a very simple band diagram like this, and the polarization does affect fundamentally the value of this, let's say, barriers. So if you have two different metals, then you have an asymmetric barrier. So, and then you have, when you switch the polarization, you manage basically to switch the entire band diagram. Okay, and that makes the average barrier higher and lower. That depends on the polarization, and then the tunneling probability is, or the effective conductivity, that is dependent on the thickness, and exponentially dependent on the thickness of the barrier, and also on the average barrier, the energetical barrier. So that's the fact. Why is happening this? What is the mechanism polarization does influence this barrier? I think is rather unknown. So there are a number of things which are now, but is not fundamentally know why is this. So, and especially for dodgy materials like lanthanum strontium manganate or strontium ruthenate, so it is difficult to say that it's pure electronic or is not structural. So we have data now showing that structurally lanthanum strontium manganate is affected by the polarization. Anyway, so coming there, so basically, what are the, and that's something rather important to analyze a little bit more into detail. What are the possible mechanisms? So an electron likes to go from one metal to the other metal if you put a little bit of field on this metal ferroelectric metal structure. So the simplest one, which happens always, is the thermionic injection. So that means that you have a certain number of carriers. We have enough energy to overcome this barrier. So, and we know that that happens also for thick barriers. So then if you apply a higher and higher and higher field on, so the barrier that becomes trapezoidal, and then you have a tunneling probability here because you tunnel through this tip. The barrier in itself, the energetical barrier, that becomes thinner, irrespective of the thickness, the effective physical thickness of the barrier. So then you have a certain field at which you onset this Fowler-Nauheim tunneling. And then you have this direct tunneling which is actually happening at very, very thin layers. So, and if you put all together, you add them, and then you calculate them, so getting some normal values from the literature, you get that picture. So we've been that time interested in calculating electroresistance. So that means is the difference between polarization in one direction and the other direction in resistance. So we call that tunneling electroresistance, but it can be also in all those three mechanisms. So, and then of course you get something like this, you see, so it's a little bit difference here. So, and the highest electroresistance you get actually for a thermionic injection. But the bad part is that you have a very low current. So it's not very useful in that sense. So, and also you see that at some point, if you increase for a certain thickness, if you increase the voltage, you onset the Fowler-Nauheim. So remember that, so I will come back to this. Anyway, that is the landscape of the electroresistance effect if you get the thickness and then if you get the applied voltage. So you see always at these voltages you have this Fowler-Nauheim, and then you have either direct tunneling, which at certain thickness is not anymore, the probability is very, very low, the tunneling probability. So, and we have checked that, so while I want just to convey this value here, so this is exactly when you switch the ferroelectrics. This is a PFM or such kind of small capacitor, and this is the current you measure on the same capacitor. So, and then you see the jump here happens exactly when the polarization switches, and this can be as high as 10 to 5. So we speak about 10 to 5, so that means it's 10 to 7%. So, and I will come back to what that means. So we have also, if we put metals which are magnetic, then you have a direct tunneling, then you have automatically magnetoresistance effect, tunneling magnetoresistance effect, which is a very well-known effect, which is very well investigated and actually is very used, or it was used in the latest hard disks. So the reader on the hard disk was a kind of tunneling magnetoresistance, that structure. That's a real device, by the way. Okay? So, and that happens just because you have the tunneling probability is modulated by the magnetization in each metal. Okay? So you have a density of states which is dependent on the magnetization up and down in the metal. So usually you have a hard magnetic metal, one electrode, and the soft magnetic metal, and the other one. This is the simplest conceptually, but in practice it's a little bit more complicated. So in such kind of structure, when we have now two magnetic electrodes and a ferroelectric layer as insulator, then you can have both ferroic parameters. So you have magnetization, which is in the metal, and you have ferroelectricity or polarization, which is in the insulator. So the insulator now is an active material, is not anymore a magnesium oxide or any dielectric, if you want. So you have the transmission, you have the tunneling magnetoresistance, where it tells you whenever you have the magnetization parallel and anti-parallel is modulated, and then you have the electroresistance, which is due to the polarization. That value here is something like 600% as the maximum. So that means is 6 times. Okay? So whereas I was speaking about 10 to 5. 10 to 5. So that means 10 to 7%. Okay? So that's the maximum, I think it has been measured now. So what I want to show you is actually the spin manipulation by the ferroelectric polarization. So if we do normal, a lland strontium manganate, which is a bottom electrode, it's very robust, it works very nice, grows very nice with a strontium titanate, and then we put just a tiny bit of lead zirconate titanate, and then on top cobalt, we obtain this multiferroic tunnel junction. And we go, so you see here exactly this, you see the PZT layers and the cobalt. So then you do both, you want to see how is this TMR, so the tunneling magnetoresistance. And it's pretty standard for this type of cobalt LSMO with a perovskite in between, like strontium titanate. So it has been studied in Paris, in Thales. So it was quite standard. So, but I'll show you the surprise we've got. So we want that, and then we tried actually just to switch the polarization. We applied some voltage. We did that, and suddenly we switch also the TMR. So that TMR, this TMR is given by the spin polarization. So practically what we've been doing, we've been changing massively the spin polarization mechanism. So because normally you won't get that dynamic switching when you have a simple dielectric instead of ferroelectric. So, and it has been shown by Di Teresa that only by changing physically the interface between cobalt and strontium titanate, you can change back to the positive TMR. This is a negative or inverse TMR. This is somehow abnormal. This is usually normal for aluminum oxide, magnesium oxide, and so on and so forth. So this is a rather robust effect, so you can switch back and forth many times. So we didn't check 10 to 7 or 10 to 8, but we checked something like 100 times, and it is working. So it has been also shown that the TMR is affected by the polarization. So Vincent is here, and I can confirm that. So it does the same. If you switch the polarization, the magnetization goes, or a TMR modifies its value. It's like it wants to go and switch in the other direction, but it seems that barium titanate has not that. Is not so powerful like PZT. But it's not only that story, and I'll show you that the polarization is not the only one. What is the mechanism here? So we didn't know at that time. So, but we talked to Ingrid Mertich, which was just across the street at the Martin Luther University in Halle, and she was telling us, "Oh, we have calculated that." So as any theoretician will tell you. So, and they calculate on iron actually. So iron on barium titanate, and we asked her whether she cannot calculate cobalt. That's indeed calculate cobalt, and everything seems to stay into this very last titanium oxide layer. When titanium is underneath oxygen, so the polarization is down, it seems that there is no magnetization of the TO2 layer. So when the titanium goes up, it seems that it creates a massive magnetization at the interface which overrules practically this demagnetization of the cobalt, and that is the spin filter is not anymore cobalt, the spin filter. So that was at that time. So I'm not so convinced anymore that it's valid, this scenario. So anyway, so if we put only lead titanate, we observe first that we have an exchange bias. So an exchange bias, it should not be, because we don't have any antiferromagnet at the interface. It might be actually a cobalt oxide here, but we have checked rather carefully by TM, there is no obvious cobalt oxide. But it might happen that the cobalt-oxygen link or bonds here, it might induce this exchange bias, which is, by the way, massive. Okay, it's half of the cobalt coercive field. So, but that is nice because from the device point of view, that can give you a nice 4-state ferroelectric spin wave. So practically, you can induce by polarization 2 states, and by magnetization another 2 states. As you see here, you have an offset in 0. So 0, the virtual 0 is here, so you have a little bit of magnetization play, so you can apply magnetic field to change this. Okay, so coming back to the mechanism, what is happening at this cobalt interface, you see that for lead titanate, so we are not having this total flip of the spin filtering. So it resembles rather Vincent data. Okay, we can go anything between the maximum TMR and about 0. So the beauty is that you can do that continuously. So if you switch a little bit polarization and then a little bit again and then a little bit again, you can get any state. You can access any state in principle between the low TMR and high TMR. But in the same time, you get also any state between low electron resistance, tunnel electron resistance, and high tunnel electron resistance. So again, these are coupled, and then it's just because it is happening at the interface. Now, coming to the antiferroelectric tunnel junction. So how about changing now the ferroelectric layer with an antiferroelectric layer? What is going to happen? So it's a very, very thin antiferroelectric layer. So, as you have seen, so if we have a ferroelectric layer here, it's rather simple. We have ferroelectricity, ideal ferroelectric loop. We have polarization one direction, polarization in the other direction. We switch, we go on the low resistive state, and then, or the high resistive state, and then we switch, we get into a lower resistive state. We stay on the lower resistive state, and then we go back in the initial high resistive state. That's quite simple. What is happening now to the antiferroelectric? So our view was this one. So practically around 0, you don't have any obvious macroscopic ferroelectric polarization. Then soon after the polarization will pop up, so you should somehow influence your barrier. So the energetical landscape should be modified because polarization is induced by the field. And then you stay here as long as when you come back with the field, you stay with this polarization until you get the lower coercive field when it gets back into the antiferroelectric state.